Hi again everyone. In this video we're going to continue our look at Laplace transforms, and in particular we're going to learn about the second shifting theorem. Now, the second shifting theorem gives us a way of computing the Laplace transform of certain types of potentially discontinuous functions. And this is important because when we solve differential equations via the Laplace transform method, we'll be able to easily accommodate discontinuous forcing functions. So this method of Laplace transforms offers a distinct advantage over the methods that you learnt in first year for solving initial value problems. But what is the second shifting theorem? Well, it's here, and it involves the product of a heaviside step function, u of t minus c, and another function, little g. Now, just to remind you what the heaviside step function is, so imagine C is a point on the t-axis. To the left of the point C, the heaviside step function is 0. To the right of the point C, the heaviside step function is 1. And at the point C, the heaviside step function is just 1/2. Now, when we multiply this heaviside step function by another function, you can think of this multiplication switching the function on and off. So in this case, the graph would look something like this. So to the left of 1, this is just 0. So we're going to get this here as our product. Now, at t equals 1, well, this is 1/2, but this is 0. So actually, the product's 0. And then to the right of 1, this is 1, and this is just, of course, t minus 1 all squared. So it's going to look something like this. So you can see here that as we get to the point 1, the function's sort of switched on, and we get the behaviour that we would expect. Okay, so the second shifting theorem just says if we have this kind of product, then essentially what we do is we calculate the Laplace transform of little g of t to form big G of s, and then just multiply through by this exponential. So let's see how this works in practice. Now you can see here, before we get to that, the shift, there's a shift occurring here. G is shifted. So this is where the shifting part of the second shifting theorem comes in. Okay, so what we're going to do is identify what's in here with what's up here, and just identify C and G of t minus c. So if G of t minus c is t minus 1 all squared, then it seems to make sense to let c equal 1, and then we can form little g of t. So what I do up here is replace t minus 1 in brackets with t and get the following. Okay, so let's calculate this. Now you can do this calculation by first principles, but it's easier and in fact standard practice to use a table of transforms. So I'm going to go down this left hand side down here. If m equals 2, then I look over here and see that the Laplace transform of t squared is just 2 on s to the power 3. Okay, so let's now form this right hand side and apply the second shifting theorem. So C equals 1. Okay, so the Laplace transform of this is just what we've calculated here. So you can see that I've clearly identified the theorem that I'm using, and we've solved that part of the question. So let's have a look at part B. In part B, we're asked to calculate the inverse Laplace transform of this expression here. Now I can still use the second shifting theorem. All I need to do is rearrange it slightly. So I would take the inverse transform of both sides and form the following. So if I take the inverse transform of both sides and rearrange, I'll get the following. Okay, so what we would like to do is compare these two expressions here, formulate C and big G, and then to get this I need to get little g of t and then shift it. So C will equal 4 and big G of S will equal 2 on S cubed. So what we would like to do is get little g of t by transforming this, and then we shift. So if we look back to our table, we want the inverse Laplace transform of 2 on S cubed. So for m equals 2, I see that the inverse Laplace transform will be t squared. Okay, so what we would like to do now is shift this C units appropriately. So let's replace t in here with t minus 4, all in brackets. Okay, so we formed this right-hand side now. So let's apply the second shifting theorem and get our final answer. Again, I've made it clear which idea or method I'm using and applying there. Okay, so we've solved our two problems. Let's look at the bigger picture. And these 2 points just have to do with method, really. So some guidelines for applying the second shifting theorem. So to use the second shifting theorem to find the Laplace transform, identify C and little g of t and then calculate big G of S. When finding the inverse Laplace transform via the second shifting theorem, identify C and big G of S and then calculate little g of t from big G of s by taking the inverse transform and then shift it. Now here's a couple of examples and exercises for you to do. It's important that you have a go at these because you only learn so much from watching. The best way to learn mathematics is to do mathematics.